Okay, we're going to go ahead and do the 16.3 to 16.4 video. This one, again, I don't think this will be too bad. We just have to introduce some of the basic acid-base concepts before we can move on and start talking about the tougher stuff, which comes kind of at the end of this chapter. So first of all, the autoionization of water. Okay, so we talked about in the last section that water is amphoteric, which basically just means that it can act like an acid or a base, depending on the situation. Okay. Now, normally it will act like an acid or a base when you put something else in there. Put an acid into the water, and the water will act like a base. Put a base into the water, and the water will act like an acid. But in pure water, just distilled water, nothing else in it, every once in a while, and this is very, very rare that it happens, but every once in a while, the water will ionize itself. So one water molecule will react with another water molecule. One of them will act like an acid and give away a hydrogen. The other one will act like a base and accept it. And then you end up with H3O plus and OH minus. So even in pure water, there is a small concentration of H3O plus and OH minus. And I mean small. It's very, very, very small. Okay? But this is called autoionization. So if you write the equilibrium expression for this process, I mean, if you look back over here, both the H2Os on the left side are liquids, so we don't include them in the equilibrium expression. Okay? So you just have the two aqueous concentrations on the right side that get put into the equilibrium expression. So then you write it as Kc equals the concentration of H3O plus times the concentration of OH minus. Okay? This is a very special equilibrium constant. It's referred to as the ion product constant for water, or Kw. Okay? So this is an equilibrium constant, but it's a special one. Okay? And so it would probably be good. Now, I think on your equation sheet, I'm pretty sure on your equation sheet, you have that number, 1 times 10 to the negative 14th, and it tells you that Kw equals that, and I think most of the equations that you're going to need to know from the next two sections here, I'm pretty sure on your equation sheet. Should have checked before I started this, but we'll check tomorrow. Like I said, I'm pretty sure that they're on there, because they almost always put them on there. So basically, the idea here with this process sorry, lost my train of thought. The other thing I wanted to say here is, and I don't think it's in these notes. No, it's not. Okay. So something else they say in the book on page 674 is that the H3O plus and the H plus concentrations are essentially interchangeable. Okay. And so you could also write this as this expression as Kw is equal to the concentration of H plus times the concentration of OH minus. Okay, they both mean basically the same thing. This one's probably a little bit more correct as far as what's actually going on in the solution, but sometimes it's easier to just write H plus rather than H3O plus. So those can be used interchangeably. It's acceptable to write it in terms of H plus instead of H3O plus. So whichever one you prefer. Like I said, the H3O plus is probably a little bit more accurate as to what's really going on in the solution. All right. They give an example in the book, sample exercise 16.4, and in that example, they basically want you to calculate the values of the H plus and OH minus concentrations in a neutral solution. Okay. So basically, if you were going to do that, and again, this is sample exercise 16.4, but we know that Kw is always 1.0 times 10 to the negative 14th. Okay? So that's equal to, if you set up the equilibrium expression for this, if you look at the equation, it's all one-to-one stoichiometry. So if H plus is x, then so is OH minus. Okay? So basically, 1 times 10 to the negative 14th equals x squared. Alright, so then if you just take the square root of both sides, that will give you the concentration of the H plus and the OH minus, or the H3O plus and the OH minus. which is going to be, you probably can figure this one out in your head, 1.0 times 10 to the negative 7th. Alright? So remember, I told you it was a very, very small amount of water molecules that do this. It's very small, so it's 1 times 10 to the negative 7th is the concentration of H plus and OH minus in pure water. Okay? So it just doesn't happen all that much. But we can actually use this kW expression even if we're not talking about pure water. We can use it if we know the concentration of H plus. Then that kW is usually right around 1 times 10 to the negative 14th. And we can usually use it even if it's not pure water. This kW still works for most of the acid-base reactions that we're going to cover in this unit. So this number 1 times 10 to the negative 14th is a very important number, because what it means is, since you always know that number, if you know the OH minus concentration, you can figure out the H plus concentration, or vice versa. If you know the H plus, you can always figure out the OH minus. Alright? Another sample exercise here, sample exercise 16.5, says calculate the concentration of H plus in a solution where the OH minus is 0.010. Let me erase some of this stuff here. Okay, so let's say that we, so what we know here is that the OH minus concentration is 0.010 molar. Okay, we also know that Kw is 1.0 times 10 to the negative 14th. Okay, so that's equal to H plus or H3O plus, however you prefer to write it, times the 0.010 molar. Okay, and so then to solve for H plus, you just divide both sides by 0.010. And that's going to give you your H plus concentration. Alright, so these are fairly simple problems. You're basically just plugging and chugging there because you always know this value. So all they have to do is give you one of the others, either the acid or the base concentration, and you can figure out the other one. And then they also give you, in a solution where OH minus is 1.8 times 10 to the negative 9th. And it also says here that in this problem and all the ones that follow, we assume, unless stated otherwise, the temperature is 25 degrees Celsius. Alright? That's kind of a key right here. 25 degrees Celsius, kW equals 1 times 10 to the negative 14th. That K is going to change if we change the temperature, because remember that temperature is the only thing that's going to change the equilibrium constant. Alright? So we're just assuming for the rest of the reactions we do in this chapter, unless it's stated otherwise, we're just going to assume they're at 25. So we can use this number, 1.0 times 10 to the negative 14th for K. Alright? So I guess the difference in this chapter as opposed to the last one is we pretty much always know what the K is going to be. Okay? In the last chapter that wasn't the case. A lot of times we were actually finding the K. But in this one, normally what we're going to be finding is the H plus or the OH minus concentration. We'll usually know the K. Alright? Alright, so as far as pH is concerned, pH is the negative base 10 logarithm of the concentration of hydronium, or again, H plus could be substituted in there. So this equation is very important, alright? And basically, this is just kind of a way to help us not to have to work with such small numbers all the time. Because when we're talking about these H plus concentrations, or H3O plus concentrations, a lot of times they're really, really small concentrations, like 1 times 10 to the negative 6th, or 1 times 10 to the negative 10th, okay? Or just really small numbers. But if you take the negative log of these numbers, then it gives you a much more reasonable number. For example, and you can just type this in your calculator, if you take the negative log of 1 times 10 to the negative 6th, it gives you the number 6. If you take the negative log of 1 times 10 to the negative 10th, it gives you the number 10. Alright? So what you can say here is if the concentration of H3O plus is 1 times 10 to the negative 6th, the pH is 6. 1 times 10 to the negative 10th, the pH is 10. Alright, so just they're easier numbers to work with, and so that's where the pH scale basically comes from, is taking the negative log of that H3O plus concentration. So again, in pure water, you've got your Kw equal to H3O plus times OH minus. Oh, I guess this is the working out of the problem, the sample exercise that they had that we went over just a little while ago. So the point is, H3O plus concentration here is 1.0 times 10 to the negative 7th. Okay. Now remember, the pH is the negative log of that H3O plus concentration. You take the negative log of that, you get 7. And that's where we get the number 7 from, where for pure water. Okay, the pH of pure water is 7. So anything that has a pH of less than 7, we're going to call an acid. Okay, because let's say that we have an H3O plus concentration of 1 times 10 to the negative 2nd. Okay, so much more concentrated H3O plus than in pure water. Well, you take the negative log of that, and it's going to give you the number 2. Okay, so the lower the pH, the more acidic it is, because the higher the concentration of H3O plus. Bases have lower H3O plus concentrations than pure water, so they're always going to have pHs of greater than 7. So they're going to have numbers like the 1 times 10 to the negative 10th that I talked about over here. Okay, that gives you a pH of 10, which is a basic pH. Alright, so then they've got this chart here that I think I referenced in your reading guide, table 16.1 in the reading guide. If it's acidic, then it's H plus, again, H3O plus, H plus, interchangeable here. Okay. The H plus concentration is going to be greater than 1 times 10 to the negative 7th in an acidic solution, which would mean that the OH minus concentration would have to be less than 1 times 10 to the negative 7th. And the reason for that, I don't want to make any assumptions here, again, if we go back to our Kw expression, right, if this number, this H3O plus number, is higher than it is in pure water, then the OH minus number has to be lower in order for this to still equal 1 times 10 to the negative 14th. Okay, so that's going to give you a pH value of less than 7. If it's neutral, they're right at 1 times 10 to the negative 7th, so the pH is 7. If you have a basic solution, then the H plus concentration is going to be less than 1 times 10 to the negative 7th. The OH minus concentration will be higher, and then you'll have a pH of greater than 7. Okay, pH values for several common substances. This is kind of useful just to kind of look at the pH of some things. Gastric juice, pretty acidic, 1 times 10 to the negative 1st, so the pH of 1. Okay, so that's pretty acidic. Lemon juice is up there, cola, soda, wine, tomatoes, bananas, black coffee, even rain, just normal rain is a little bit acidic. Saliva is acidic, kind of makes sense, break down our food. Milk is acidic, just barely. Human blood and human tears fall just barely on the basic side of things, just a little bit below the 1 times 10 to the negative 7th. And then everything down at the bottom, egg white, seawater, baking soda, borax, milk and magnesia. Milk and magnesia is something you can take when you have stomach issues, because a lot of times it will settle the acid in your stomach because it's a base, and the base will react with the acid and neutralize some of the acid. But after you get past milk and magnesia, you're getting into stuff that you probably don't want to ingest anymore. Lime water, household ammonia, household bleach, sodium hydroxide. Definitely don't want to ingest those things. So the more basic it gets, the more harmful it gets. But we eat a lot of acids and bases, acids all the time. Bases tend to be more for maybe medicines and cleaning and those sorts of things. I don't think there's anything else I need to say about that. Now, P, basically, all that means is to take the negative log base 10. Okay? So you could put P in front of anything, and it would mean take the negative log of that particular number. Alright? So there's a couple other ones that are that are useful for us. pOH is the negative log of the OH concentration. So instead of just pH being the negative log of the H plus concentration, pOH, take the negative log of the OH minus concentration, and that will give you a number similar to pH, usually within the 1 to 14 range. pKw is the negative log of your kW expression. Now, kW number, I guess. Now your kW number is 1 times 10 to the negative 14th. Okay? So your pKw is going to always be 14, because you take the negative log of 1 times 10 to the negative 14th. That's just going to equal 14. Alright? So the nice thing here, I don't know if they have it on here or not. Oh yeah, they do. Okay. So H3O plus times OH minus equals kW, which equals 1 times 10 to the negative 14th. Alright? We also know that the negative log, if we just basically negative log everything, and I don't know if you remember this about logarithms or not, but when you have two things multiplied together like this, and you take the log of both of them, then you end up adding them together in the expression. So you've got negative log of the H3O plus concentration plus the negative log of OH minus. And then we take the negative log of the kW side as well. And the negative log of kW, like I said before, is equal to 14. Alright? So pH plus pOH equals 14. So let's say the pH is 3. Okay? If the pH is 3, then the pOH must be 11, because they have to add up to 14. Alright? So that's kind of a handy expression to have here. If you take the negative log of both of the values, they should add up to 14 at the end. As far as measuring pH, you could use litmus paper or an indicator, and those are less accurate measures. We've used indicator already this year, and that's a good way to get a general idea of what the pH is, but it's not going to give you an exact number for pH. It's going to be a little more qualitative than quantitative. Okay, and again, that's basically all we've done so far this year. But if you want more accurate measurements, then you can use a pH meter, and that measures the voltage in the solution, which is related to the ions in there. And the ions will tell you basically how much of the H3O plus you have running around in your solution, so then you can measure the pH. We are going to use pH meters, I believe, for our next lab. Yeah, we are, because we need to know what the pH is in our next lab. So, and we need to know it exactly. So we're going to use the pH meters for that, and they're really easy to use. They hook up to the vernier stuff. But that's a way to get a more accurate pH measurement than just using the litmus paper or the indicators. Okay, that's as far as we need to go. Now, I do want to talk about maybe a couple of things here. Let's see, we got a sample exercise. Calculate the pH values for the two solutions described in sample exercise 16.5. So you go back to 16.5. You've got a solution with a concentration of OH minus of 0.010, and they want you to find the pH of that solution. Okay, so what we had to do in 16.5 was figure out the H plus concentration. That's what they were initially asking us for. Okay, so if you have, let's see if I still have this worked out back here. I don't think I do. I think I erased it. Oh no, I didn't. Okay. So basically what you're going to do to find the H plus concentration in this problem is take 1 times 10 to the negative 14th and you're going to divide that by 0.010, which is going to give you 1 times 10 to the negative 12th. Should have been able to do that in my head. 1 times 10 to the negative 12th is your H plus concentration. Okay? To find the pH of something, I'll just do it on this screen here. To find the pH of something, remember the pH is the negative log of the H plus concentration, which in this case is 1 times 10 to the negative 12th. Okay? So the pH of this solution would be 12. Alright, that's a high pH, which would mean that this is a fairly basic solution. Okay? So, let's look back here. See if that makes sense. Our OH minus concentration was 0.010. Our H plus concentration was 1 times 10 to the negative 12th. So if you look at that, the concentration of OH minus is much higher than the concentration of H plus. So it makes sense that this would be a basic solution, that it would have a high pH. Okay? Now, another thing that we need to talk about is, this is kind of random, but it's the way you do sig figs when you're working with logarithms. Okay? So, in your pHs, you're going to, basically, the only sig figs that count are the ones after the decimal point. So right now I have no sig figs in my problem, because this first number, if you think about it, is essentially just telling you your exponent. Okay? So what you have to do on these sorts of problems, let's go back here and look at, it looks like we had 2 sig figs in the original question. Okay, 0.010, 2 sig figs there, because this second 0 is significant. So we need 2 sig figs in our answer for pH. So let me make sure this is, yep, that's the way the book does it too. Okay. So basically with pH, this is what you have to remember, and this is important, and I'll probably reiterate this in class. When you count the number of sig figs that you need for your answer for a pH, that's how many decimal places you need to have in your answer. Okay? So again, the 12 doesn't count because it's really, that's telling you the exponent. The 2 numbers after that are telling you your number of significant figures. Okay? So that's just kind of the convention with pH. You have to be careful with that. That will trip you up from time to time, I'm sure. But that's the basic idea there with what you would do. Okay? So basically, I don't think you're going to have a lot of trouble with these problems, because it's all just manipulation of the equations. Now, the next sample exercise, 16.7, they give you the pH and they want you to calculate the H+. It might be worthwhile real quick to just go over how to do that. So, if you've got a pH of 3.76, so we already know this number, and we want to know the H+ concentration. Well, that might seem initially a little bit tricky, right? So what you basically have to do here is, and I don't know if you remember this from math class, but to get rid of your log, if you have a log on both sides of the equation, you need to 10 it. I don't know if that's really what it's called, but that's what I always call it. You 10 it, okay, which means that you raise both sides to the power, you raise 10 to the power of both sides of the equation, alright? So first thing I want to do is get rid of the negative over here. So I'm going to just transfer sides on that. 3.76 is equal to the log of H+. Okay? And then what you want to do is you're going to 10 both sides. So now I've got 10 to the negative 3.76 is equal to 10 to the log of the H+ concentration. Okay? Now, since log is base 10, when you take 10 to the log of something power, then this part basically cancels out. Alright, so then what you end up with is, sorry, I'm trying to find space to write this, 10 to the negative 3.76 is equal to your H+ concentration. Basically just cancels out that log part. Okay? So basically to solve for those kinds of problems you have to 10 it. So then you take, in your calculator, you just punch in 10, use your caret button. On this one, you actually have my permission to use the caret button. I know I said never ever use that, but this year you can. And now I actually can't find mine. Not finding my caret button. But I don't really need it because it's right here in the book. So what you're going to get when you take 10 to the negative 3.76 is you're going to get 1.7 times 10 to the negative 4th. And that's your H+ concentration. Okay, so that's how you work backwards if you're given the pH and you're trying to find the H+ concentration. Now, let's see. It doesn't look like they give you any other sample problems there. Other than give it some thought, if the pOH for solution is 3, what's the pH? Should be able to figure that out in your head. It would be 11.00 because it's got to add up to 14. So those are the kinds of equation manipulations you're going to have to do on this one, and I don't think you're going to have too much trouble with it at all. All right? Okay, so that's autoionization of water and pH.